The next thing we're going to be looking at is chemical reactions. These occur when bonds are formed, rearranged, or broken, and usually represented in chemical equations. You might see reactants, products, relative amounts of each, or states of matter in a chemical equation. Here are two examples of chemical equations. For the first one, we have two hydrogen atoms as the reactant, and then on the right, we have the product, which is H2 or hydrogen gas. For this reaction, we've combined two hydrogen atoms together to be hydrogen gas or a molecule of hydrogen. For the second reaction, we see four hydrogen atoms combined with one carbon, and we see all those atoms represented in methane or CH4. Because molecular formulas must be written correctly and account for all atoms, we'll see by using chemical equations that matter can neither be created nor destroyed, and if a chemical equation is written incorrectly, it may suggest that. But we want to make sure all atoms must be accounted for. Let's look at a couple of types of reactions. First is the synthesis reaction or combination reaction. An example, very simply, is A plus B gives me AB. That involves a bond formation. These types of reactions are always anabolic. They're building processes where you put in energy to form or create a bond. In these reactions, we usually have atoms or molecules combining to form larger, more complex molecules. An example of this in the human body is amino acid molecules coming together to form a protein molecule. The creation of peptide bonds between these amino acids is a great example of this synthesis or anabolic building reaction. The opposite of a synthesis reaction is a decomposition reaction. So let's take AB as a molecule and break it down to its constituent atoms, A plus B. So a decomposition reaction is going to always break bonds and therefore release energy. These types of chemical reactions are always catabolic or degradative, so they're the opposite of synthesis. A good example in the human body is glycogen, where you take glucose or sugar molecules and break them down into their parts. So breaking down glycogen into glucose molecules is an example of a decomposition reaction. But more often than not, we see exchange or displacement reactions, where we have both synthesis and decomposition. So you have both building and breakdown, or anabolic and catabolic. And that's where bonds are made or broken. And when you're writing ions or ionic bonds, when looking at these chemical equations, make sure you're always writing the positive ion first. An example of this in the human body is looking at ATP and its breakdown, and the addition of the breakdown or break off of a phosphate from ATP and its addition to glucose allows for the oxidation of glucose and for it to help us power cells and power their metabolism. So keep in mind when we're talking about chemical reactions, we have introduced some terminology like catabolic for degradative or breakdown reactions, and anabolic for building or for creating bonds types of reactions. We also can use terms like exergonic for reactions that result in a release of energy, or endergonic for reactions that result in an absorption or use up of energy. But all chemical reactions, regardless, are going to be theoretically reversible, even though we don't always write them that way. That's because a chemical equilibrium does exist. Oftentimes, if a reaction doesn't occur in both directions, it's because you just generally have more product or reactant in that situation. So keep in mind that chemical reactions are oftentimes presented as balanced chemical equations. And while many biological reactions are not very reversible, theoretically they could be if the proper situation and circumstances were involved. So in summary, catabolic reactions are degradative reactions. They involve breaking bonds by using water, usually to dissolve a bond. That's a hydrolysis reaction. And they're exergonic. They release energy. So when you break bonds, energy is released. Anabolic reactions are synthesis reactions. They're combination reactions. They're the opposite of decomposition reactions. They involve making bonds. And if breaking bonds releases energy, you store that energy or put it into making a bond. So they're endergonic as opposed to the exergonic catabolic reactions. And one of the last things we'll talk about is just how are reaction rates affected by things like an increase in temperature or a decrease in particle size, or a change in the concentration of a reactant. We're going to look at reaction rates because they're affected by things that we talk about repeatedly. Things like temperature, particle size, concentration, and the presence or absence of a catalyst, which is also known as an enzyme. When we're talking about chemical equations, how quick that chemical equation converts reactants to products is its reaction rate. If you were to increase the temperature of a reaction, atoms move around quicker and are more likely to interact, therefore increasing reaction rate. If you decrease particle size, those reactants of a chemical equation can move faster because they're not weighed down, they're not large. So that can increase reaction rate because you're more likely to see those atoms interact. And an increase in concentration of a reactant just crowds an area of reactant. You're more likely to see interactions among those reactants, so that will increase reaction rate. And last but not least, catalysts, which are also known as enzymes or biological catalysts, they can increase the rate of a reaction without being used up by that reaction. So enzymes can be used over and over again to make sure that reactants come together to produce products, and they'll do so in order to make a reaction quick enough to sustain life. So that's just a quick look at chemical equations and reaction rates. Next, we're going to be talking about things like amino acids, which build proteins, and monosaccharides, or simple sugars that build carbs. So stay tuned for the rest of Chapter 2.